Hello everyone and welcome to this video. In this video I'm going to show you how to model, well, this little beam in ABAQUS which is supported by two springs and a line load as shown there. I'm going to model this using a beam elements, and also the stiffness K I'm going to take as 50 meganewtons per meter. Okay, so let's get started. So, to get this out of the way, and so open ABAQUS, always start with parts, create a new part, call this beam again. Gonna use a 2D planner, 2D model in this case, so you select 2D planner and wire element. The thing is 5 meters long, so I'm gonna keep the approximate size as 10 because it puts the origin in the middle of the beam. And yeah, so you click continue, and then we draw a little line, just a line in this case, so it's a line which is 5 meters long, so I type 5 and enter, and there's my line, and I click escape and put all in the middle with this little red option, auto fit. There's our 5 meter beam. That's all I'm drawing at this point, so we click done, and that's beautiful. And yeah, now we need to do section assignments and so forth. So we double click on section assignments, then I'll select the part, drag and drop, so we call that thing set beam, click done. We need a section, so we create a new one, create section, gonna make a beam element, so beam section, call it beam section type beam, because we're gonna model bending as well, so we call beam section, and we say continue. And also for a profile, so we need to create a profile in this case, click on that thing, let's make it a rectangular profile for simplicity, so just call it rec profile, so continue, A and B, so it's indicating on the sketch what the dimensions mean, so let's make it a 300 by 500 mil section. So just to say again, I use standard SI units, so meters, newtons and pascals. So you click OK, that's my profile and selected by default. Need a material, let's say it's a steel section for some reason, name it steel, say mechanical, elasticity, elastic, Young's modulus 210 gigapascals and Poisson's ratio 0.3. Not that it will make a difference in this model, but it still needs to be filled. Say OK, everything selected, looks fine, say OK. Beam section selected, great. So there's our beam. Then when we created our beam, if we're modeling beam specifically, you need to assign beam orientation, otherwise the model's going to moan about it. When you get to the end, it's going to ask for beam orientation. How you do that is when you double click on section assignments, these options pop up, and that little thing with the N and the T is the assign beam orientation option. So you select the regions to be this assign beam orientation, so we can select our set, which is beam, and that direction is fine for positive, so you usually just select enter, and we agree with that core system, so we say okay. So that's great, and we can dismiss this thing because we already assigned our orientation. Now to see if it's correct, we can always go to display mode, view part display options, and we're going to say on general we can select idealizations, render beam profiles, and then it actually renders the profile. So if you have different profiles, you can see how the orientation is actually interpreted by ABAQUS. But yeah, when you model I sections or so, it's more important. But let's just show you, is now you can actually see the section of the beam in this case. Just gonna go to X, I want to rotate to the X. Anyway, so now we're just gonna remove this thing because I like my line. Bar display options, remove that, say okay, we have our line again. Wanna change my view to what I had. Not as easy as it looks. So rotate something like that seems okay to me. Okay, just fit it, so there's our little beam again. Now I've assigned sections and assigned orientations. Now we need to insert our little springs at the support, so we can go expand engineering features and we say springs and dash spots. Double click on that. Now you say, let's call it spring. So the same stiffness is applied to both sides. So we're gonna, and we always, our springs are connected to ground, so you're gonna click connect to ground, say continue. Select the first point and the second point by holding the shift key. Both are red, so both are selected. Say done. Then it asks the degree of freedom. It's going to be 2 in this case. It gives me 1 which is axial, 2 which is bending, and 3 or 6 is the rotational degree of freedom. I'm going to select 2 because that's in the y direction. And the stiffness I said is 50 meganewtons, so that's e to the 6 meganewtons per meter, and that's okay. And see the springs are inserted. Next, after the springs, we move to our mesh. So double click mesh. First seed the part. Global size you can select. If you select a size which is bigger than the actual beam, then it's actually just put elements at its end. So let's say my beam is 5 meters long, so let's make our seed size 6 for example, and then just put seeds at the end node, which is fine for my little model. So we're going to mesh it. Okay, to mesh the part. Great. Now let's say if you want for a beam, you can select element type, select our beam. Then it gives us, well, select beam element. So shear flexible is by default. ABAQUS uses the TM'sChannel formulation. And if you want the standard Euler-Bernoulli beam, you can just select the cubic formulation. 2-node linear beam in plane, 2-node cubic beam. Yeah, just a difference. Keep note of that. So you can. I'm happy with the way as it is. Now it's set up. Go to assembly instances. Yeah, you want to bring all our parts in there, which is just the little beam. Put it there. Now we need to create our load step. Let's call it load. We don't need boundary conditions in this case. Explicit boundary condition because our springs are connected to ground. Say load. That's fine. And now we apply our little line load. So you see our line load goes from that node downwards. So for that you need to create a field in ABAQUS, what they call a, well, field, and an analytical field. So you can double click analytical fields and we can call it line load. It's an expression field. We can say continue. Then it gives us this little option, so you can now say, well, in terms of x and y, with reference to this coordinate system, what is the equation of this line over here? So this line would be y equals to 120x well, on that side it will be x is equal to minus 120x. Well, 120y. Y is equal to minus 120y. So for this model, pause net hierso. So the equation of this line, with the origin taken as that point, is y is equal to minus 120,000 newtons per meter plus 600,000 kilonewton. So that equation is the one we enter here. So y equals is by default entered. So you can just say minus 120 E3 times x plus 600 E3. And we select our global coordinate system, and that's it for the line. Now our line equation is defined. Now we need to create our load. So we go to loads, load step, call it triangle load, and it's a line load, in this case mechanical. Say continue. And the bodies for the load is our beam. Well, you can select the set we created already, just the beam set. Continue. It's red, and system is global. We use the line load distribution, and component 1 is in the x direction, which in our case is null or 0, and the y direction it's 1 because our value is already interpreted by the equation itself. So you can just say OK, and there's our load. Well, I should probably make the component negative, so you can just right click, edit the loading, and say component is -1. Okay, and now our load is, well, looks alright. Yeah, and that's just how you enter the triangle load. Another way you could do that, I'm just gonna suppress this one for now, is by creating a new coordinate system at that point and defining it as the origin for the lines equation. How do you define a new coordinate system? Well, you use this, or you can go to tools, datum, and select CSIS or C-size, I don't know how you should pronounce that, and then you can create coordinate system from 3 points, 2 lines, or offset from coordinate system. In my case, I'm going to select one by using 3 points and use the option there, which is create datum system principal axis or 3 points, which gives you all the offset or 2 lines. So I'm going to use the 3 point option. Let's call it datum system 2. Find rectangular coordinates, say continue. Point to be the origin, select that point. Point to be on the x-axis, so you select positive x-axis this direction, and we just say create datum, and we don't want to create another one. And there's our secondary axis, which we are going to use now for our next load, or redoing of the load. So we created the load again, so load, let's call it triangle 2, triangle, line load, continue, region selection, select the whole beam, which is fine. Oh, sorry, we still need our analytical field to be created. So what you can do is, if you forget things like me, you could just select the create analytical field option there, call it line load 2, expression field, continue, and then where it says global or local system, you can either create one with that option, or you can just select them. One thing is important to remember is once you created one, you should still select it. I keep forgetting that option. So name is fine, we just select this coordinate system. See, it's datum system 2, and now the equation is, well, y is equal to minus 120,000 times x. Is it a minus? No, it's positive. I'm sorry. It's positive. It's upwards. And that's it for this case. So we say OK. And now the component 1 is still 0. Component 2 is minus 1, because it's still in the negative direction. We say OK. And that did not work for some reason. Let's say edit. Oh, because I created my field but didn't select my lineload 2's field. So let's try this again. And there we go. Sorry. So once you created something, you should select it. Otherwise, you run into trouble. So this is two equivalent loads, just different ways of creating them. Okay. And if you want to remove something from the analysis, you can just, well, suppress it by right-clicking and say suppress. Then it's not included in the analysis. Yeah. So if I unsuppress both, the load is going to be effectively doubled in this case. Okay. So yeah, there's springs and springs and line loads. I'm just gonna, for completeness sake, carry on and create a job. Let's call it job 1. That's fine for now. So that's also fine. I'm gonna submit it. Hopefully I didn't forget something. You usually get this thing when you select the default job, so it's okay. Override, submitting. Oh, I actually forgot something. I'll show you now when this thing stopped running. For beam elements, it's actually useful to add field output request for moments and stuff. So we're going to go to field output requests, double click on that, double click on that, and when you go to not stresses, forces and reactions, you can select N for something, nodal forces in beam section orientation. That gives you the local forces for beam elements, which is quite nice if you want bending moments and shear forces and such. So we say okay, now we rerun our job, otherwise this field is not going to be included. So you say submit again, overwrite the job files, submit it, it's running. And it's completed. Going to look at the results. So here's our displacement. You can put both shapes there. So you can see the thing literally just moved downwards. I think the reason one part is not moving more with each other is because I chose just one element to model it with. So let's just increase the mesh size and see how that influences the results we get. So I'm going to go to my meshing options in my model. I'm going to reseed the parts. So seed, and instead of 0.6, let's make it 0.5. Apply. Yes, we want to delete the meshes. Looks a little bit better. So in general, the more elements you have, the more accuracy you get, but don't make it too fine, otherwise you're just, wasting. So let's just mesh the part again. Turns that turquoise-ish color. And now resubmit the job and see how that influences. Yes, overwrite the job files and see how our result improves by using more elements instead of just, well, one. Hopefully you'll see a difference. It's completed, so you click on results, say deformed shape. Now that looks a lot better, so you go to displacement, Y displacement, see the spectrum is a lot better now. So yeah, again, increase that font size. You go to viewport annotation options, legend, set font. Once we're at 14, let's make it 18. Now it's very big, so everyone can see your results. Now, one thing for beam element which is nice, you can actually see the bending moment and shear force diagrams. If you, well, that's in so 1 is the axial forces, 2 is the shear forces, and 6 is the moments. The reason 6 is because for a 3D frame element, that moment is going to be the degree of freedom number 6. You can actually see the moment, or have the moment plotted on the beam if you do this. That's our undeformed shape. So you go to result. You go to contour options, and this thing pops up, and you just select show tick marks for line elements. You say apply, and there's our moment diagram for this loading condition. And it makes sense because our springs are pinned, or effectively pinned, so you have 0 moments at the ends and the moments distributed as such. Shear force, as such. Quite a nice representation, and axial forces none. Well, you can see it's effectively 0, it's just numerical indiscrepancies that cause, well, the axial forces to do this. I mean, 10 times 10 to the minus 11 is effectively 0. Okay, so thank you very much for watching. I hope this video helped you, and happy modeling. Thanks.